First of all, if suppose this is one-dimensional manifold, this is one-dimensional manifold, then the simplest difference is seen that what is the dimension of this guy? The direct sum. No, it's one. Because imagine you have one circle, for example, and the other circle. So your manifold consists of the point belonging either this circle or this one. And so it's characterized either by some, it is always characterized by one variable. When we have the direct sum is either m or n. The direct product is m and n, so to say. So, in other words, well, you may actually forget about it. You are just saying phi is, either you say phi is equal to phi 1, which characterizes it, or phi 2. Now, going back to this picture, we say that what does it mean to glue this thing? When I say identify or I glue this thing, what do I mean? Or what do I mean it here? It's easier. The easiest is to answer in terms of possible functions. What are physical possible functions on a sphere, on a circle? How you can characterize which function f of phi are meaningful in the sense that they are uniquely defined by the point on a circle. The function means that you take a point on the manifold and then you yeah, they must be periodic. And f of phi plus 2 pi is f of phi. The set of such functions define the manifold. You can define, instead of saying we have a circle, you can say we have a set of functions which are periodic. Now here we have a set of functions which are periodic with respect to two variables. Okay, now one more example before we go back to physics. So here we have the torus by considering this function. Again, the torus can be just defined as a manifold on which the set of function is periodic with respect to two variables. We have another two-dimensional object, a compact object, which is what? What would be another natural topology? Sphere. But how to, on a sphere, you have two angles, azimuthal angle and polar angle. And so you have to consider functions f of theta and phi. And but now sphere, of course, if you simply demand periodicity, it will be something wrong. It will not be a sphere. A sphere cannot be equivalent to a torus, right? So what do you think we should say? I remind you that phi changes from 2 pi to 0. Theta changes from pi to 0. So when we have a sphere, which is what I'm talking about is just that both a torus and a sphere are generalization of a circle, in a sense. Two-dimensional generalization of a circle. So what kind of functions are allowed on a sphere? First we could draw a picture. Phi changes. We have this This is pi. And this is 2 pi. Now, yeah, go ahead.
You need to bring all 4 points to a pole.
Yes. How I do this?
You need a function where they're all, and you identify all the points.
Well, it's a correct start, but you still have to finish.
So you need a function whose value at all 4 points is equal.
Yeah, actually, what
F of 0, phi is equal to F of 0, 0.
actually a little more than that, but you are almost right. If you have theta equals pi, then it should be phi independent. It must be a constant. This is what it corresponds to in and f at theta equals 0 is also a constant. It could be a different constant, actually. What this point is geometrically? It's a North Pole. On the North Pole, compass doesn't work. That's what it says. It doesn't know where to look. And this is the South Pole. So the functions, and also another thing which you need to require is, of course, that f of theta and phi plus 2 pi is equal to f of theta. And indeed, that means that you identify all, you have a square, and you identify all 4 sides as one point. So that's the way you describe manifolds. And that we now return to our case, and we will need this understanding. What is called n-dimensional torus is just the product of n circles. And and once again, you obtain it by considering, say, a cube and identifying faces of the cube. So it's all very easy. Direct sum, by the way, as you see, is purely one-dimensional manifold. It's just collection of circle number 1 and circle number 2. Okay, so we have a motion, just like a harmonic oscillator moves on a circle, system with 2 dimensions moves on a torus. And before I analyze this motion, I want to give you some example of dynamical systems on a torus, which are not trivial. But even before that, I want to say that, as you see from here, if the system is cast into this form, you have AIs. You have, in 2 n-dimensional phase space, you have n commuting conserved integrals, because they are canonical momenta. So if the system can be rewritten in terms of action angle variables, then it contains n commuting conserved integrals. And turns out the converse is also true. And this is an interesting theorem to which I could, in some versions of this course, I actually showed how to do this, but it will wear a bit short of time. So if you are interested, the idea of proof is not difficult, but the theorem is this. The theorem is that suppose you have a dynamical system. It's called the Liouville theorem. And as I said, the proof is not difficult, but it takes some time to explain. By the way, one more comment about Liouville. The statement, we before had the statement, I think I forgot to say this, the statement that under canonical transformation, the phase volume doesn't change. This is also called the Liouville theorem. So you encounter this name. It's like when you look at the names of various theorems, you see that same names appear again and again. And someone said that it's like 10% of people drink 80% of beer. And the same name, Liouville, Lagrange, Euler, they appear again and again in this course. Anyway, the Liouville theorem says that if you have a system with some function, where you have some function of P1, Pn, x1, xn, such that they are conserved, so fk dot is 0, and that's important, the Poisson brackets of these two functions are 0, and they are functionally independent. So you don't want to have function f2 to be a function of f1. Under this condition, there is always possible to find action angle variable. You see, they commute, but you have to find some combination of f so that I phi j will be delta ij. That's non-trivial, but so like all those functions, it moves on a such this system's called completely integrable. And as I said, the surprise, the reason why I'm talking about it is that they are extremely important, and there are many highly non-trivial systems in nature. I will give you, by a little later in this course, I will give you some highly non-trivial example from hydrodynamics where complete integrability holds. So, returning to those things, we want to know. Yes, I wanted to give you a few physical examples. So, a trivial example is this. Let's take the Hamiltonian in 2 dimensions, 2 space dimensions, with spherically symmetric potential. So examples. Is it completely integrable or not? I'm asking the question. And if yes, what are the which functions we should use as? We need 2 commuting integrals of motion for complete integrability, because there are we have 2 n-dimensional phase space. The phase space is 4-dimensional here, n is equal to 2, and so too we need 2 integrals. What are, if they are there, what are they? Well, I guess from the way I phrased it, it's obvious that this is completely integrable. But still, what are conserved integrals?
P1 squared plus P2 squared.
By itself, no. If you take only this guy, it will not commute with this, and it will not be an integral. It will not commute with. So the integrals commute with Hamiltonian. By the way, when I'm saying one more important comment is here k is 1 to n, and one of these functions is a Hamiltonian. So Hamiltonian is included into this n function because it commutes with itself, obviously. The question is, what is this? So here we need the second integral, the second conserved integral. What is the second conserved integral here? So we can always say f1 is h, and f2 should be something which we briefly discussed actually already. What kind of symmetries as conserved quantities we have here?
So you want things like angular momentum?
Yes, I want things like angular momentum, which we called L, and which is P1 x2 minus P2 x1. Now, imagine, so these are, it's conserved, of course, because of rotational symmetry. And you can just commute it with the Hamiltonian and see that it is conserved. You have rules of the game are well defined and simple. You just calculate the Poisson brackets. You calculate and you find that it commutes with the Hamiltonian that we already discussed last time. And see how non-trivial it is. We said that a completely integrable system moves on two-dimensional torus. So from here we can, what does it mean? It means that suppose that we take a surface, so we have four-dimensional space, and we take a surface, then the Hamiltonian is equal to energy, some numerical constant, and L of P and X is some other numerical constant. This defines a submanifold in our four-dimensional space. In our four-dimensional space, this is how many dimensions this manifold has? 2, because we have two constraints in four-dimensional space that defines two-dimensional manifolds, defined by these algebraic equations. It is far from obvious that this manifold is topologically a torus, but it is. That's the consequence of the Liouville theorem, that since we can, by change of variable, continuous change of variable, bring it to this form, we have the motion on the torus. And in this case, we have two-dimensional torus embedded in four-dimensional space. It's not a, you see, just like in one dimensions, we said that in the phase space it is this is a topological circle, or this is, if you don't know how to draw, you can always declare your pictures to be topologically something. That's I will be doing. So this is a circle. And this will give us some torus, which also will be drawn in this way. And without the Liouville theorem, it's far from obvious. Now, one more example. We will study this motion on the torus just a little later. Before that, I give another example. Let's look at the following. Let's now take six-dimensional phase space. So another example, six-dimensional phase space. here things are slightly less trivial than in 2 dimension. I claim that this system is also completely integrable. That is, it has 3 commuting integrals of motion. And I want you to try to figure out what it is, what they are. So here we managed to construct 2 integrals of motion. They commute. Everything's nice. What are, apart from h, what are some obvious integrals of motion here?
Could you clarify what you mean by integral of motion?
Oh, okay, sorry. Good that you always interrupt me when I use some term is unclear. Integrals of motion means simply a function on the phase space, which you take a solution of equation of motion, and its time derivative is 0. There are many synonyms for this, many names. It's called conserved integrals, conserved quantities, integrals of motion, maybe something else, but don't be, I hope you're not confused with it. So it's basically a thing like energy which doesn't change when the system moves. So some function which is, and here I also was talking about those functions which don't change with time. So the condition that the function is an integral is simply that it commutes with the Hamiltonian. So that's, are you satisfied with it? Okay. Okay, but now your turn to, now that you know what is the integral of motion, you have to tell me the formula for it, or what kind of integrals of motion we have in this case.
It will be L1, L2, L3.
Yes, okay. So at the first glance, we have too many integrals of motion. In this, as I said, for integrability, you need 1/2 of the phase space. The phase space is 6-dimensional. The 1/2 is 3, so we need 3 integrals of motion, and we already have 4. In fact, there are even more sometimes than that. But there is a problem here. What is the problem? It's not a solution. It's not the answer.
Do they not commute with each other?
They do not commute, exactly. Yes, exactly. They do not commute with each other. So we need to do the following. We have h. This is one integral. Conserved quantity, one conserved quantity. We have, say, L3, which commutes with h, and we need something more. And what we know is that L1, L2 is L3, L2, that's a commutation of rotations. L2, L3 is L1, L3, L1 is L2. So we have these non-zero commutators, or Poisson brackets. That's also another synonym. I'm sometimes saying Poisson brackets, sometimes I'm saying commutators. It's the same thing. All right, so we need one more. You see, one more which will commute with the Hamiltonian and with L3. guess what it is?
L squared.
Yes, actually, if you take, very good, if you take L1 square plus L2 square plus L3 square, you will see that by commuting using these brackets, you will see, first of all, the fact that it commutes with Hamiltonian is obvious, because this is time independent, this is time independent, this is time independent. They all commute with Hamiltonian. So L square H is 0, that's obvious. What is slightly less obvious and requires some calculations is that L square and L3 is also 0. So in this case, you have complete integrability, and in 6-dimensional space. Once again, when you fix this, so the complete set of integrals is this. And when you equate it to some numerical values, you consider in the whole phase space, you again consider submanifold of the phase space. So you say H is E, L3 is something, L squared is something. You get how many dimensions? What is this hypersurface submanifold which we get by fixing? So we have H, we say it's E, L3 is L, L square is, I don't know, N. These are numbers, and these are functions of P and X in 6-dimensional phase space. So, yeah, there are 3 constraints on 6 coordinates. So generically, it is 3-dimensional hypersurface immersed in the 6-dimensional phase space, and which is defined by these algebraic equations, which are complicated. And once again, miraculously, the alluvial theorem tells you that this hypersurface is topological torus. It's not a torus in a smooth sense, but it's just like this circle is deformed, but it is continuously deformed to a real torus, which is a nice thing. And now we will see how to analyze the motion on a torus of completely integrable system. But I must say that complete integrability, that is, once again, not to let you forget, it's just in 2n dimensional phase space, you need n commuting into another name is constants of motion. That's I hope will not confuse you too much. So the integrals, constants of motion, integrals of motion. There are so many ways people are using. It's all widely used, all of them, all the terms. All right. So when you have this thing, it's an exception, not a rule. That you have this. If you go, for example, for 8-dimensional phase space, if you have 4 x dimension and 4 p dimension, and suppose we keep this rotational symmetry, it will not be integrable anymore. There will not. It's a mirror. It will be integrable for particular potentials, but generically, it's not generic at all. All systems in 1 dimension are integrable. Spherically symmetric systems are integrable in the case of 4-dimensional phase space and 6-dimensional phase space, but that's it. as you go to 8-dimensional phase space, generally they are not integrable. And it was quite a hunt for integrable systems which started in the 19th century and continued on a completely different level, which by some methods which are fascinating, and I intend to tell you about them. For example, with this method, just to give you a taste of what will be coming later in the course, we will look at the system with 2 n-dimensional phase space, and for which the Hamiltonian is this. This system first appeared in plasma physics, and it's called the Toda lattice. It describes ions in plasma, etc. Naively, if you use just Noether's theorem, all you have here is just what kind of naive integrals you would ascribe to this system, or conserved quantities. So this is Toda lattice. And this is the example which we will work out later in the course. But at the moment, I'm just asking you a very modest, very simple question. If you don't know anything about hidden structure, there is a huge mathematical hidden structure in this Hamiltonian, highly non-trivial. But suppose, which is the case, we don't know about it. What is the naive integrals we would say are there? What Noether would say? Well, first of all, it's Hamiltonian, right? So Hamiltonian is conserved thing. What else? What other symmetry? There are some obvious symmetries there, and symmetries, as we know, generate conserved quantities. Yeah, go ahead. Yes, which leads to conservation of what?
Linear momentum.
Which?
Linear momentum.
Yes, it's you can easily see that sum of pk is constant as time, and h is constant. So something which begins with p and p squared is constant. Now, the great surprise which follows from almost nowhere is that there are n integrals here. The next integral will be like sum of pk to the cube plus a lot of stuff, and we will see how to find them. And this system turns out to be completely integrable. So that's another completely integrable. That's the discovery of the 20th century. Actually, the integrable system, modern integrable system, is a discovery done here in Princeton by Martin Kraskell and others in the 60s, in the 1960s. And it's turned around all mathematical physics, actually. It's created. It was extremely important discovery. And what is surprising is that it started as some problem with in the plasma physics. But we will be talking about it, discussing solitons, etc. All this is connected to this. At the moment, I just want you to just get the feeling of those things. And now let's discuss a very important feature of it, namely which relates it to statistical mechanics. How am I doing with time? Yeah. We will introduce one more important concept, the concept of ergodicity, which is characteristic for dynamical systems. ergodicity and entropy, that's what we're going to discuss. So, ergodicity is just a rather fascinating feature, which tells you that if you have a motion that under certain conditions, which we will specify, we take some periodic function, the function, our phase space now is a torus, as we discussed. And we take the function of angle variables, the coordinate space, and we want to consider this function changes with time. So f of t is f of phi1 of t, phi2 of t, phi n of t. And as the system moves, it changes quite in a complicated way. But now let's consider its time average. Namely, we have to solve solve these equations of motion and pass to angle variables, and now we take the limit. We define the average in a very natural way. We simply take the limit t to infinity, 1 over t, more generally, when you have the phase space, an arbitrary phase space, you always can define time average. So you have f of pi of t and xi of t. The time average is and that's basically if we think about the gas, what we measure, since our devices have characteristic times for reaction, which is much larger than intermolecular time, time of atomic collisions, etc. It's clear that what we're really measuring are time averages. When we so the infinity here means simply time much greater than the time for molecular interaction. The question is how to calculate it, because if from definition it seems terrible. Actually, here we have the function which depends on 10 to 23 variables for a gas. Now, what is remarkable, though, is that this thing can be calculated quite efficiently. Let's start with harmonic oscillator. Not harmonic, with one-dimensional system, excuse me. In the one-dimensional system, so 1D. In one-dimensional system, average of some function will be f of phi of t dt from 0 to t, 1 over t. And you probably can tell me what would be the intuitive answer for this average, for this time average. What is the probability to find a particular value of phi, which is what we want to do? Let me explain maybe more, a little bit more. What we want to do is to replace this time average, which requires solution of equations of motion, which is possible here, but generally impossible. We want to replace it by some average in the phase space. And roughly speaking, the statement I'm going to discuss is that time average are equal to phase space averages, and that's the basis of statistical physics. What would be, before we prove things, what would be the intuitive answer here when this, just visualize this particle rotating around the circle and so on? No, why zero? It's phi is, of course, oscillates, but it depends on the function. It's not zero. It could be zero for some functions, of course, but generally speaking, it's something. So what is given is a function f of phi. And I want to know how to average, how to make these averages.
1 over 2 pi after phi is phi.
Yeah, it's basically, how would you explain? That's the right answer. How would you explain this?
So phi dot's constant. If dh di is constant.
Yeah, and
so
phi dot is constant, yes.
And so d phi is equal to phi dot dt.
Yes.
And so
Okay, I see. But let me make life more difficult for you. Let's simultaneously think about the answer for this guy. How about that? What would be the answer in this? Try your method in this case. Here you gave absolutely correct answer, namely, but I think well, it's simply the integral d phi divided by 2 pi f of phi. And now you have to give the multidimensional analog of it. You have function of n variable and you integrate.
Can we just do the integral for each dimension?
The what?
The integral for each dimension.
Yeah, the answer will be, I give you the right answer, and then we will interpret it, and then we will derive it. The answer is this. So the answer tells you that time average is equal to the average over the torus. You have a function on a torus. This integral is just the average of this function over the torus. The probability, it simply tells you that probability to have to be at certain phi 1, phi n is a constant everywhere on the torus. And to understand it, you have to visualize what happens generically with the trajectory. So imagine that there are certain, for this case, there are certain conditions under which this ergodicity is. So we have ergodicity. Time average equals phase space average. And notice that indeed here we need to solve the equation of motion, although for integrable system we can do it easily, but still here there's no information about equation of motion. You just take the function and integrate it over the torus, and that's it. And also notice one more peculiar thing, that here you have n-dimensional integral, here you have one-dimensional integral. So in a sense it's a very counterintuitive before you visualize the reason for this statement. So how visualize, say, let's begin with two-dimensional torus. How the particle moves on the, what's the trajectory on this two-dimensional torus?
So this would only work if omega 2 and omega 1 are not related by a rational.
Yes, that's what I said, that there are special conditions under. Okay, I think you are practically there. So you are right. We need omega 1 and omega 2 to be incommensurate. So it's irrational number. If it's rational, it's a different story. So, but there are much more irrational number than rational. So it's not a serious constraint. But why? Explain why. What's the intuitive origin?
If there's a rational and rational, then after one of them goes p periods, the other one will go exactly q periods.
Yeah, but suppose it's irrational, then what?
Then those cover almost every spot.
That's right. What's happening? This trajectory winds around the torus and never returns to the. It never closes. And finally, it starts covering the torus more and more densely. So in the limit, it will be simply the integral over the whole torus. And now we derive it and see how. It's surprisingly simple thing to derive. You see, when we go, yeah.
How does Poincare recurrence happen here when the frequencies are incommensurate? Because it seems that
You start with a certain point, and then the trajectory will never close, but it will come closer and closer to this point. So what Poincare recurrence says is that not that trajectory returns precisely, but it can be arbitrarily close as the time goes. But that's a good point, and this system, I have to warn you, that's not yet statistical mechanics. The system we are looking at, the ergodic theorem is an important element of statistical mechanics, but there is much more to be checked and proved before we conclude that before we derive Boltzmann or Gibbs statistical mechanics, which we will do. But all right, now how to prove it? Let's start with harmonic oscillator. The very convenient way to prove is to say that the arbitrary function can be expanded into a Fourier series. It's sum over n, some function fn e to the I n phi. So there is the rather simple mathematical theorem is that any periodic function with smooth, provided that it has nice smoothness, etc., differentiability, that we assume that everything is as differentiable as needed. So this function can be presented as a linear combination of the elementary, you have elementary periodic function where n is the integer. And turns out there is a completeness theorem that this set is complete. That is, any function can be expanded linearly on this set. It can be viewed geometrically as an expansion in infinite dimensional space, but that's kind of obvious. All right. Now we use this, and we find that f is equal to 1 over t integral over dt from 0 to t. And here I will have sum over n, f and twiddle, e to the I n phi. And here I put omega t. I'm working out now one-dimensional case. Multi-dimensional case will be similar. So we have sum over n, f and twiddle, 1 over t, integral from 0 to t dt, e to the I n omega t. And that gives us f and twiddle, 1 over t. We have 1 over I n omega. And here we have I n omega t minus 1. So I just calculated this integral. Now if t goes to infinity, it seems that the whole thing goes to 0 because this exponential is bounded. 1 is bounded, but t goes to infinity. But this is almost right, but not quite. There is one term in this sum which survives the limit. Most of the terms will go away because this 1 over t factor here, and because of the fact that this is a bounded function. It's just cosine and sine, right? So it doesn't become large, cannot compensate the largeness of this. So but there's one term which remains, which is what? N equals 0, right. So that you can see either from here by expanding n equals 0 or simply integrating n equals 0 term. So we come to the result that it is f0 tilde. Okay, but what is f0 tilde? Take the integral f of phi d phi divided by 2 pi from 0 to 2 pi. And this is f0 tilde. Only the first term will contribute. So we proved for one-dimensional case, this is proved. We have this ergodic theorem for harmonic oscillator, meaning that, or one-dimensional system in general, meaning that this one-dimensional system simply winds around the circle, and it visits each point of the circle with equal probability. That's the point, that there is the circle is completely homogeneous, and probability to visit the interval d phi is d phi divided by 2 pi. So that's it. Now let's do it for it's clear from our discussion that there should be slightly more tricky in higher dimensional case. So let's do the same thing in higher dimensional case. Same story, except we now take f of phi. I'll call it a vector phi, meaning by a vector phi 1, phi n. And the same Fourier decomposition, but now you have vector n. N is n1, nn. F tilde n, e to the I n phi. Now we're repeating the same thing here. We get average is 1 over t, integral from 0 to t. We have e to the I. Let me start writing again. So f is sum over n, Fn tilde integral 1 over t integral dt from 0 to t e to the I n omega t, which gives us, so far everything as before, except we use vector notations. 1 over t and now we're, same formula as before. Now you probably can see what's happening, what will contribute to this formula. And it should account for the comment made that you need incommensurate frequencies for ergodicity. This feature, I probably already said this, feature is called ergodicity. It's written here. Time average, phase space average. Okay, so where is this commensurability condition or incommensurability condition? We again send t to infinity. Again, exponential is bounded, it's just sines or cosines. So it's tempting to write down that it is f0 twiddle. And this would be correct for incommensurate case, for irrational, if the ratio of frequencies is irrational. But how to see this from the formula? You should be able to see this from the formula. When the argument breaks down, just look at the formula and you will see when what is the dangerous part in this formula, which can, if everything is finite here, then 1 over t will kill the whole thing. But what can save it? Simple question. Yeah, go ahead.
And then W and an omega normal.
Yes, you see that then if n omega is 0, then we have to account for this contribution. But if the ratio of frequencies is irrational, then it will never be 0 except for n equals 0. Okay? So, if omega 1 divided by omega 2 is irrational, then f is just d phi 1 d phi n 2 pi to the n f of phi 1 phi n. So it's just the average over the torus. If it is not irrational, then we have to pick up extra terms, and ergodic theorem breaks down. It will not be the whole torus which is covered. Okay. Now, you can actually, I suggest it as a home exercise to pick up the contribution of the points. Suppose that omega 1, omega 2 is p divided by q, and you will be able to see from this sum the naive geometrical idea that it is, in this case there are closed trajectories and not all torus is covered. All this should be seen from this thing. All right. Now, the reason why it is so interesting is that it tells us that, at least for this class of systems, that if you have a function on the phase space, and you take its time average, as we will see next time, it's simply if there are in the generic case, it's equal to the it's proportional to the dp dx, but multiplied by the delta function that h px is equal to e, and we have the function f of p and x. And from here, so that's what ergodic theorem said, that time average is equal to the phase space average, provided that we get this. This is what is called microcanonical Gibbs distribution. And it is the basis of statistical mechanics. However, we will see that there are a few more things which are needed for statistical mechanics, which we will discuss next time. Today, I just want you to appreciate that there is a very simple theorem, derived very simply, at least for the integral system, which is foundation of statistical mechanics. But there are much more which is needed for statistical mechanics, and that we will discuss next time. So let's stop here, and please ask questions. There is nothing difficult in this part. It will be much more tricky when we will be discussing the growth of entropy and things like that. This is just a peanuts comparison. But still, please ask questions if you have some. Yeah?
When you did the H equals E, L2 equals some number, and L sub 3 equals some number.
Yes.
How would we convert from those to the I's and Phi's?
That's a very good question. And the question is basically that you have those conserved quantities which depend on p and x. And the alluvial theorem simply says that there exists a transformation of variables which lead us to ik and phi k. And your question is how to find this change of variables. That's a great question. The answer is that, in the 19th century, the answer was unknown in general. People managed by just trials and errors. For example, one famous completely integrable system is a rotating top in gravitational field, and it was discovered by Sofia Kovalevskaya, whose portrait you can see on the third floor. She just by trial and error found the change of variable which leads. Now, that was the 19th century. In the 20th century, there was the so-called method of inverse problem, etc., which we will discuss, which I alluded to discussing the total lattice, which allows us to, it's highly non-trivial, but it allows to construct explicitly the action angle variable. So your question is difficult. It's not something which even geniuses of the 19th century could do in general. And they thought, actually, I think common thoughts up to the middle of 20th century was that it's impossible to answer this question in general. So the answer is sit down and calculate. Try this and that and so on. Now there is a technique involving algebraic geometry, a lot of stuff which allows us to do this. That was a great progress in mathematics.